Welcome to Introduction to Area Under a Curve. Before integration was developed, people found area under curves by dividing the space beneath into rectangles, adding the area and approximating the answer. Right, so now notice here we have a curve, right, and it's divided into rectangles. Well, notice there's some parts under the curve that aren't part of the rectangle. So our answer is not going to be exact because we're missing all of this space there. That is under the curve, but not inside a rectangle. So as the number of rectangles n increases, so does the accuracy of the area approximation. The rectangles more closely approximate the curve. I'm just waiting for the page to change. There we go. So we're going to be dealing with continuous curves. So if f is continuous, by the extreme value theorem, which we learned about in curve sketching, on any interval AB, f obtains a maximum value on AB, and f obtains a minimum value on AB. And so notice I have the bottom of a rectangle there from 1 to 2. Now let's say I want to represent the area under the curve from 1 to 2 as a rectangle. Right, so now do I go to the maximum value? Right, so if I go to the maximum value, I have this rectangle. Notice that we've got all the curve in the rectangle, and then we've got some parts that aren't in the curve in the rectangle. Or do I go to the minimum value? Right? Do I go this direction instead, and I go where the value hits the minimum on the curve? So do we end that rectangle where the minimum value is? And then I've got parts of the curve that aren't represented. I don't have any overlap, but I do have some parts that are now missing from the rectangle. Well, which one do I use? Well, it depends which type of approximation we're going to use. The red one is a left Riemann sum. It's also called I don't use this name as much. I usually use a Riemann sum. So that's the more traditional term. Now they call it left rectangular approximation. I like Riemann sum personally. So if I want to do a left Riemann sum, which means I'm going to use wherever the left side of the rectangle hits the curve, I would use that maximum in this particular example. If I wanted to do a right Riemann sum, which is now called a right rectangular approximation. I like Riemann sum. Right, there we go, rectangular approximation. I would use where the left side of the rectangle hits the curve. There's no wrong answer here if they're both correct. Just depends. Are we going to use a left sum or are we going to use a right sum? Right? In this particular example, the left Riemann sum is going to overestimate because it includes the rectangle includes area that is not under the curve. If we use the right Riemann sum, then we're going to underestimate because we're missing part of the curve. But either one of those could be used, and we're going to learn how to use both of them. And maybe I should change the page before I plan to change the page. I know we'd change it too early. So if we divide an interval into n subintervals, we could call each one the ith subinterval, right? Because we're going to need to break up our area into subintervals, right? If we just use one big rectangle, we will probably have a really bad approximation. The maximum value that f reaches on the ith subinterval is called f with a capital M. So here, if we look back at the example on the last page, the red box, there we go, the red box is using f maximum. It's using the maximum value for that particular rectangle. Right? And then the green box is using F minimum. Right? It's using the minimum value for that particular rectangle. And on any rectangle, we have a maximum and we have a minimum. Right? And it depends which type of approximation method we're going to use. That tells us whether we're using the maximum or the minimum. And the left won't always be the maximum, and the right won't always be the minimum. Depends which way the curve goes. All right, so inscribed rectangles, they lie inside the subregion, and they have a height, in this particular case, because they're inscribed, they're inside, they'll use the minimum value. Right? So this particular rectangle has a height of 1.6. The height is the y value. Or the value of the function for some value of x, whatever the x value happens to be. Right? And then the change in x is the difference between the x values. In this case, and we'll look at how to calculate that. In this case, the change of x is 1. Am I going to finish the rest of my, what happened to the rest of the word? There we go. All right, there we go. Circumscribed rectangles. They extend outside the subregion. So in other words, the curve is inside the rectangle. Right? So the minimum value is 1.6. The maximum value is 2.75. Actually, it looks like, yeah, I guess I call it 2.75 for the same interval. And so it all depends. Do we use the minimum? Do we use the maximum? Right? And you'll know which one to use, right? Because you'll be told. Do a left Riemann sum, do a right Riemann sum. Right? So finding the area of each region is easy with rectangles because the area of the rectangles is really easy to find. Right? So, and these areas can be added to approximate the area of the function. Now, sometimes we'll have to add up all the rectangles individually because they'll have different widths. That happens more often in a real-world problem where our intervals aren't always nice, little, even. We can't always just say, hey, let's just make each change in x be 1 or 2 or whatever, right? So let's make this many rectangles. When we have real-world data, we're sometimes limited by what the intervals are. And we'll see that not in this video, not in the next video, but we will eventually see. We'll eventually work with real-world data. Right now, you're just learning the basics. All right. So if you look on this chart, and by the way, make sure you're taking notes as you go along. All right. So and these are important things. So the height is the value of the function f of x. The width is the change in x. All right. So that's our change in x. And it'll be the difference between the values that make up any one rectangle, particularly when they're not all the same width. Now, the rectangles don't have to be the same width, but it's a little easier if they are. So when we can, we'll make them the same width. So usually Riemann sums or rectangular approximation will use equally sized partitions of the interval to make the calculations easier. By having bases of equal length, the base can be factored out when calculating the sum. So in other words, we can add up all the heights and multiply it by the change in x, the base, one time, as opposed to having to do it for every single rectangle and then add them together. And we'll do a few problems on this video. There'll be more on the next video. And there we go. So an introduction to area under the curve. There are 3 methods that we can use to find the, actually there are 3 methods. Yeah, there's 3 types of Riemann sums. So it's actually, if you want to think of it that way, there's 5 methods. There's the Riemann sums, it takes up 3 of them. And then trapezoidal rule and Simpson's rule. The only one we're not going to do in this class is Simpson's rule. You'll do that in Calc 2. Right, but we will do the other ones. We'll do the 3 types of Riemann sums. We'll do trapezoid rule. And in this series of lessons, we'll do that. So for each method, we have to know the same pieces of information. We have to know the function of the curve. Either we're given a graph we can use, or we're given an equation. We need to have something. We can also be given a table of values. That would also work. And then the x values would be the x values from the table. The change in x would be the width between those x values, and the value of the function will just be, the value of the dependent variable. But that's for a while, not for a while. Let's stick with graphs right now and equations. And then we need to know the boundaries on the x-axis for which we're finding the area. You cannot work with an infinite amount of area, right? We need to have very precise x values, right? We have to have a start and a stop, all right? Otherwise, we have an infinite amount of area. Oh, and then if I didn't say it, we need to know the number of partitions or rectangles. I think I may have skipped that one. Right, so here, how do we find change in x? So if the subinterval is 6 units long, and we want to divide it into 12 subintervals, the change in x would be 1/2, right? Because we would take the 6, it's 6 units long, right? So in the numerator, we have the endpoints of the interval. Here we're told 6. So most times you'll be given just the start and the stop. Right? So here we're given the 6. We divide it by the number of subintervals. So that means each interval is going to be 1/2. If the interval is 0 to 2, and we want to divide it into 5 subintervals, then we would take and let me put change of x here, so this is change of x. We would to find the change in x, we would take the difference, since we're not given the length, we're given the 2 endpoints. 2 minus 0, larger minus smaller, and then divide it by the number of subintervals. So that would give us 2/5, right? And that's how you'll always calculate amount when you have partitions of equal width. Okay. So right down here, we got information about change in x that you should make sure it's in your notes. So change in x is the length of the base of the rectangle, or the width of the rectangle, or whatever you want to call it. And it's found by taking the endpoints of the interval, taking the difference between them, and then dividing by the number of subintervals. This is always a positive number, right? So it's always large minus small. All right, so rectangular method, divide the interval AB into n pieces. Each piece has the same width. Right? So the change in x is b minus a divided by n, right? Because b and a are the endpoints, and n is the number of pieces, the number of rectangles. And I'm going to show you here what it looks like, and I have some notes for you. What it looks like to do, what the left-hand Riemann sum looks like, the right-hand Riemann sum, and the midpoint. Right, so add these all to your notes, and I know they're in your notes. Right, so f of x, of course, is the height, right? And if it's a left Riemann sum, the height is the left endpoint. Right, so that means the height here, and I'll do this one in blue since I wrote in blue, is the left endpoint. So the left side of the rectangle. When the left side hits the curve, that's the rectangle. Same thing for the next one. When the left side hits the curve, that's the rectangle. So notice in this example, the left one is the larger, the smaller side. Because if I had done the right side, it would have been larger. And then where except for maybe this one, left one hits the curve, that one actually overlaps, goes outside the curve. The other ones were inside the curve. And then where the left one hits, excuse me, I'm done. Did I get them all? No, sorry, we have one more rectangle. Where the left side hits. Sorry, I stopped too soon. I have to go all the way to B, right? So we would use these values. So it's going to be, so let's call this one, let's call that x1 and x2 and x3 and x4 and x5. So for the left Riemann sum, we would have f of x1, which happens to be f of a, right? So actually, I'll let that just be a, since it's since it's already got an a there. So we would use f of a plus we would use f of x2. We would use f of x3. We would use f of x4. And that's it. Notice 4 rectangles, 1, 2, 3, 4, 4 values. Now we would take that value and we would multiply it, so if I can get this to move because I need a little bit more space. There we go. We would multiply it by the, can the equal sign move? No. The change in x. All right, so I want to focus on the y coordinates first. The heights of the rectangles. Now let's focus on the widths. So this would be equal to the change in x, which would be b minus a divided by n. And we would multiply whatever that value is times all of these heights. Right? So we'd add up all the heights and we'd multiply it by the width one time. And then we don't have to distribute it and do it to each one. Right? That's just extra work. Right? So the height is where the left endpoint, the value of the function where the rectangle hits the function on the left-hand side. Right? And that's how you find the left. That's how you find what values you're using for the left-hand Riemann sum. Let's look at the right-hand Riemann sum. There we go. All right, so here we are using the right endpoint. All right, so now it's where the right side hits. All right, so I'm going to go from the right. All right, so here's where the, oops. The right. I think I used the same picture. So ignore the blue and red rectangles. They didn't mean anything to the right-hand Riemann sum. Right? So now the right hand is using the larger values. Right? So I'm going to go to where the right side of the rectangle hits the curve. I don't care about the left. The right, so this one's shorter. And the right. Right? So these would be the rectangles that I would use for the right-hand side, right? For the right Riemann sum. Right? And so the height is the right side of the rectangle. It's the value of the function on the right-hand side. So that means that the area here, again, we still have our change in x. So b minus a divided by the number of subintervals. In this case, actually, we know what the number of subintervals is. So let me just change the n, since we actually were given n. In this case, it's 4. Let me change it on the other one as well, since we know it. Any day now. Oh, good. Spinning ball of death. I was hoping I'd have a spinning ball of death. There we go. So let's change that n to a 4, because in this case, it is known. You'll always know the number, unless, of course, it's just a sample to show you what to do. Like we don't know what b and a is, but you would if this were a problem to do. And what happened here? Well, that just doesn't look good. So let's just redo that. Can I erase that? Okay. So let's make that b minus a divided by 4. And as soon as that ends up there, what the heck? You saw that, right? I'm not imagining things. What on earth was that? I have never seen that before. I'm scared what I'm going to get now. Okay. Phew. I have never seen a red, look like a red ellipse. I've never seen that before. A tic-tac, a red tic-tac. What was that? All right, so it would be b minus a divided by 4. And then here we would not be using a. We've got x2, x3, x4, just like before. We're going to use f of x2 plus f of x3 plus f of x4. And now we'll use plus b. Actually, excuse me, f of b. You got to plug b in. You're not going to use the x value. All right, so you're using, you're using these values here. I won't write them in. It's kind of hard for me to write f of b next to that because it ends up right there. All right, so, but that's how we would calculate it, because we would use where the right-hand side hits the curve. All right? And when I draw the rectangles, if I'm using a left Riemann sum, I draw the rectangle starting at the left. If I'm drawing a right Riemann sum, I draw the rectangle starting at the right, so I go to the right place. Otherwise, I'll look at my rectangles wrong. And here is the next one. So now this is a midpoint. Right, so of course ignore the blue and the red rectangles because they have nothing to do with this. Right, they were the left Riemann sum, but we're going to use the same curves just so you can see all three of them. All right, so again, f of x is the height, is the value of the function, but now it's the middle of the rectangle. We want to find where the middle of the rectangle hits the function. All right, so I'm going to label these the same values as before. Excuse me. So we had this being x2 and x3 and x4. So let's call we want the value in the middle here. Oh, let's call that x1, I guess. It's in between. So we want where the halfway point, yep, come on, there, it hits the curve. There we go. So I've hit the curve. That means that's where the rectangle is going to go. Now, interesting on the other ones, it was either overlapping or it wasn't big enough. Notice this one has a little bit we're missing and a little bit that's not under the curve, that's in the rectangle. Right? I wonder if those two kind of cancel each other out. All right, so now let's call this one x 2.5. Right, so now it's where this value hits the curve. And there we go. All right, so it goes right there. So notice I'm missing some curve, but then on this one I'm mostly just missing. Well, actually my rectangle's a little short because my line stopped. So let me fix that. Because we should have some that's overlapped, some that's in the rectangle but not in the curve. Let's make that a little higher. There we go. And some that's in the curve but not in the rectangle. That looks a little better. That's closer. All right, so now let's do the same thing over here. Let's call this one x 3.5. And so we would use this value. And I'm going to try to make sure I stop in the right spot. It's hard to tell because I'm waiting for the line to catch up. All right, so it's where, and then when I go to draw it, it's never exactly, not always exactly where, like that is not exactly in the right spot. So just because I know where I want it to draw, the top of this rectangle, but it doesn't mean it'll be there. All right, so it's where that line hits the curve. All right, and so this would represent our third rectangle. And again, notice we're going to have 4 rectangles, 4 sums. Oh, I didn't do that on the last one. I'll go back to that one just to show you. 4 rectangles, 4 sums. All right, so here where let's call this one x5 let's just call it x5, right? Because we don't have an x5 anyway. So I don't need an x4.5. Let's just call this x5. Right, and so it's where this one hits the curve. Oh, that looks pretty good, except for at the end there, it did a little whoopee thing. All right, so the values we would use, right, the area is approximately still the same change in x, b minus a divided by 4, and then we would use f of x1. Notice I did not use a, right, because that's not in the middle, plus f of x 2.5, the one in the middle, plus f of x, what was it, x 3.5. and then plus f of x5. Notice, great numbers here. We did not at all use, any parentheses, we did not at all use A or B because those are endpoints and we want all middle points. But notice we have 4 sums because there's 1, 2, 3, 4 rectangles. So if we have 4 partitions, we need 4 rectangles and 4 sums. And let's go back to this one. I didn't do the 4 here. I didn't mark the rectangles. So now if we look at our sums, any day now, right? So we look at the sums, right? We've got 1, 2, 3, 4 sums and 1, 2, 3, 4 rectangles, all right? So make sure your partitions matches the number of rectangles, matches the number of sums. Those have to be the same. All right, and we're going to do a few more together before this video ends. Just waiting. Oh, did I hit? I thought I changed the page already. So this, by the way, is a really, really big concept. All right, the ones coming up are huge concepts that you'd have to make sure you understand. All right, so the area of the rectangles, the area is approximately going to be the height times the width of each of the rectangles. All right, the width is the change in x, the b minus a divided by n. And then this one happens to be a left Riemann sum. We're using the left endpoints. Right? So we're using f of a, because that's a left-hand Riemann sum. So right, this is where the left side hits the curve. And then we're using f of a plus w, because that's where the left-hand side hits the curve. And if you can guess what the w means, it's a plus 1 width. And then we're using a plus 2 times w. Right, that's where the third rectangle, on the third rectangle, that's where the left-hand side hits the curve. And then we're using a plus 3w, 3 widths, and it's where the left-hand side hits the curve. Notice we never use b. You never use the upper endpoint if you're doing a left Riemann sum, right? Because that's on the right-hand side, not the left. All right? And that's all there is to these, right? But then now we're going to do a bunch of them. Now that you got the idea, but that's the basic idea of how to do them. And let's see if we have one coming up. All right, so we'll go over a little bit, and then we'll have some. And so, oh, by the way, this is important. So put this in your notes. This is important notation. You have to be able to use the correct notation. All right, and you have to be able to understand the correct notation. All right, so when we find the area under a curve by adding rectangles, the answer is called a Riemann sum or a rectangular approximation. Sometimes they call it RAM, rectangular approximation method. The width of the rectangle is called a subinterval. If we use subintervals of equal length, then the length of the subinterval, which is the width is the width is going to be the change in x, which is just the upper value minus the lower value divided by the number of rectangles. The definite integral is given by the area under the curve and the number of rectangles. So now let's look over at that notation there. And so, the area under the curve, I'm sorry, I meant to go over here. I kept reading, and I'm like, huh. So it is given by the area under the curve, but this is where I meant to be reading. All right, so let's look at the notation here. So this goes right here. I should put an arrow so I don't read the wrong direction. All right, so let's look at each little part. All right, so we're taking a limit. As n goes to infinity, that means that n there is the number of rectangles. That's what I'm trying to point out to. So n here is the number of rectangles. And so we have an infinite number of rectangles. All right, so as we have an infinite number of rectangles, or the sigma, this means sum. I'm going to add some arrows in here, right? And we're starting with the first value. So this happens to be a right Riemann sum. This is the heights of all, and it doesn't matter for this if it's right or left. So we're adding up all the heights of the rectangles. So the f of ck, that's the heights of all the rectangles. F of c is the value of the function. F of ck is the sum of all the values of the function. Right? So f of c is just one value. F of ck is all of them added up. So it's the heights of the rectangles times the width of the rectangles. Right now, we are just doing the summing part. The heights of the rectangles times the width of the rectangles, and we do not have an infinite number. Once we find the limit and we have an infinite number, we have the exact area under the curve. It'd be the definite integral, and it's the exact area under the curve. Right now, you won't really need this notation so much as we're talking about the Riemann sums, but we're going to come back to it, so remember that, okay? All right, so if you have questions, let me know, and it might be that I answer your questions as we move on, all right, and we come back to that concept. So if it's not completely clear in your mind, if some parts of it are clear, that's good. If it's not all completely clear, but you've got it in your notes, then wait till we come back to it, and when we come back to it, and we're finding exact areas rather than approximations, and it's still not clear, then let me know. And so if f is continuous on AB, and the value of the function is greater than or equal to 0, all right, so we're looking at positive values for all x in our interval AB, then the area between the curve y equals f of x and the x-axis over the interval, so we're looking at the area from the curve to the x-axis. That's defined by a equals the limit as n approaches infinity of, and then n, so we're summing up all of the heights of the rectangles. This part here, the change in x, that's the width of the rectangle. This is all the heights of those rectangles. We're summing that up. And it's as the number of rectangles goes to infinity. What happens to the width of our rectangles as the number goes to infinity? Right? So we have a finite space, and we're putting more and more and more and more rectangles. Well, those rectangles are going to get skinnier and skinnier and skinnier, and our width is going to go to 0. Right? So that's something to be thinking about as we move on in this topic. But right now, let's take a look at just finding a Riemann sum, right? And just being able to approximate the area, because that's important too. And there we go. All right, so finding the area under the curve. We're going to divide the interval 0, 2 into n sub-intervals. In this case, n is going to be 5. You can see we have 5 bars. This one happens to be a right-hand Riemann sum. There are inscribed rectangles because they are inside the curve. And notice that all these all the y values are where the right-hand side hits the curve. So notice the rectangles are drawn, so the right-hand side is hitting the curve. And we want to approximate that area using a Riemann sum. Now notice, and then I need one more, right? So I'm using 1 value, 2 value, 3 value, 4 value, 5 value. Know which value I don't use? I don't use A, right? So we are going to use, and I don't even know what we're going up by a fifth, but we already have the y values. So but I'll put the x values here so we can talk about what values we're using. We're not using 0. That's not being used. Our change in x is 2/5. We are using 2/5. We don't have to plug it into anything. We don't even have anything to plug it into, but we do have the y value up there. We are using 4/5. We are using 6/5. We are using 8/5. And we are using 2 because they're on the right-hand side. Right? So our area is approximately the change in x, which is 2/5, times, we're going to add up all the heights of the rectangles that we got from the right-hand side. So we would add up 4, and I think I had this change, yeah, I'll leave it as a decimal. You know what, no, actually I'm going to change that to a fraction because it's easier for me to deal with that 2/5. And I can multiply fractions in my head. I get to decimals and it's not as easy, especially as I get 2 decimals and all that. All right, so the 4.8 is 24/5. The 4.4 is 22/5, The 3.8 is 19 fifths, right? 15 fifths plus 4 more. And the 2.4 is 12 fifths plus 5 fifths. Right, so we're going to add up all the heights and then we'll multiply them one time by the change in x. So 2 fifths times, so that would be 80, add those all up, we get 82 fifths. And then we're going to multiply by 2 fifths, and so that's going to be 164 25ths. So the area under the curve is approximately 164 25ths. That's the value of, this is the right-hand Riemann sum. Right? Notice that this area, this is an underestimate. Right? So the area, and I don't have the notes in front of me. You follow along and you add things, and you see as I'm writing stuff down, you might think, oh, that might be important. So the area, make sure you have somewhere in your notes that the area under the curve, in this particular case, is an underestimate, and the part we really need, if this problem's not in your notes, then you can leave that part off, but you definitely want this part, that if we have a right Riemann sum, and the function is concave down, the estimate is an underestimate. So that is very important to know. I think I'm going to have to move this one. I can't fit underestimate on that line. I'll just put I'll put is over here. Can I fit that? Yeah. And maybe I can fit underestimate here. All right, so here's our first example. All right, so we can definitely see it's an underestimate, but anytime you have a function that's concave down and we're doing a right Riemann sum, our sum is going to be an underestimate because the left-hand value is greater. That's because it's concave down. It's decreasing. All right, let's take a look at the next one. And it's going to be the same function, but now it's going to be a left-hand. There we go, a left-hand Riemann sum. All right, so now we would use 0. We would use the 2 fifths. We would use 4 fifths. We would use 6 fifths. We would use 8 fifths, but we would not use 2 because that's on the right-hand side, and we want the left-hand side. All right, so the area, and actually I'm going to use this for area. Right, so the area is 2 fifths, and then times, right, so we have the 5 would be 25 fifths, 4.8 would be 24 fifths, the 3.8 would be, the 4.4 would be 22 fifths, I'm ahead of myself, the 3.8 is 19 fifths, and the 2.6 is 13 fifths, and we would add those up. So that would be 2 fifths times 103 fifths, which is 206 25ths. So now notice that now we have a larger value, and we can see that there are parts of the rectangle that there are parts that are not under the curve but that are inside the rectangle. So the left Riemann sum and when f of x is concave down is an overestimate. Right, so now we're overestimating. Right? So sometimes it's going to be an underestimate, sometimes it's going to be an overestimate. And actually, if we had more rectangles, we'd actually be a little bit more accurate. But 5 was good on this one. I think I have a few more for us. I don't think I didn't have a midpoint on that one. Oh, there we go. I don't know what happens when my board freezes. How about now? Change in X? And the recording freezes. Oops, and then we got lots of change of X. And then all of a sudden it shoots up again. Do I talk really fast? What happens then? All right, so we have change in X is 4 minus 1, and we want 5 rectangles. So that's going to be 3/5. How about the writing? Let's see. Come on, this is like one of the last ones I'm doing on this video. Let's see if we can get through it. Come on, board. Oh my gosh. I guess, maybe because I had the pen in my hand when I was erasing. Let's try that again real quick. Come on, change in X equals 4 minus 1 divided by 5 equals 3/5. Okay, there. That looks better. All right, so the heights of the rectangles are what we get when we plug the values in. All right, so these are left-hand Riemann sums. Right, so we are going to use 1, and these numbers are here really hard to see, but we are using 1. That's our starting value. All right, and then the width is 3/5. So this would be 1 plus 3/5. So this would be 8/5. So you can see it kind of right there. So I know this one looks like f of 1/2, but it's not. It's f of 1. So we have f of 1. We have f of 8/5 on the left-hand side. Right, that's where the rectangle hits. We would be plugging in another 3/5, so that would be 11/5. So each one of these has a width of 3/5. So you generally use that fact, especially if I have a fraction here, to just keep adding 3/5. So 11/5 plus 3/5 would be 14/5. 14/5 plus 3/5 would be 17/5. We don't use the 4 because the 4 is on the right-hand side. So then we plug those into the function. Right? So we have f of 1. Well, that's pretty easy. 1 squared plus 1, that's going to be 2. It won't take up much space to do that. F of 8/5 is going to be 8/5 squared, so that would be 64 20/5 plus 1 would be 25 20/5, so that's going to be 89 20/5. So this is the height of the rectangles. And I know it's going to take up some space, so I started it down there. I don't know if I'll have enough space for it down here, but let's try. F of 11/5 would be 11/5 squared, so that's going to be 121 20/5 plus another 25 20/5 for the 1 would be 145 20/5. Now that does reduce, no, excuse me, never mind, 146 20/5. Wondered about that. Because 121 20/5 didn't reduce. Didn't think that was right. And so there we go. But even if it did reduce, we wouldn't reduce because we want to be able to add them together. F of 14/5 would be 14/5 squared, so that's 196 20/5 plus 25 20/5, so that's going to be 221 20/5. And then finally, F of, who was the last one there? 17/5. All right, that would be 17/5 squared, so that's going to be 289, right? 289 20/5, yeah, plus 25 20/5. All right, so that would be 314 20/5. Lovely numbers here. All right, so the area under the rectangle is approximately, so our sum here is going to be, we're going to take the change in X, the 3/5, and then we're going to multiply that by our sum, and we're going to add the 2. I'm going to change the 2 to be over, have a denominator of 25, so that's 50 20/5, plus 89 20/5, plus 146 20/5, plus 221 20/5, plus 314 20/5. All right, and then we would add those up, right? So that's, and then we'd multiply. So that's going to be 3/5 times, now I'd like a calculator, please. Whoops, got a bunch of stuff in here. All right, so this would be 50. Actually, I'll just add the numerators. 50 plus 89 plus 146 plus 221 plus 314. That just doesn't, I guess it does look like a 25. Would be 820 25ths, which I'm assuming I typed the numbers right into a calculator. We could reduce, so this would be 3/5, then times, they're both divisible by 5, right? So that would be 820 divided by 5, that would be, I'm going to do it faster with the calculator. 164. Whoops. Start to make a 5 there. 164 fits. So that would be, oops, I made a 5 anyway. There we go. So that's 492 25ths. That's our answer, right? So sometimes the computation gets to be a little much, but it's really not too difficult, right? And that's our steps for a left Riemann sum. Right? Let's see. I have an ending point. I think the next one is an easy problem. If so, I'm going to go very quickly through an easy problem. Yes, we have one easy problem. That's going to end our video. Calculate Riemann sums for the function f of x equals x cubed on the interval 1 to 5 using 4 subintervals. And it's using left endpoint, then we're going to use the right endpoint, then we're going to do a midpoint. So just noticing our interval, 5 minus 1 is 4, divided by 4 is 1. So that already is pretty simple. And it's only x cubed, so I'm plugging in integer values. And I actually have it all done because these values were just so simple. All right, so here's the left-hand Riemann sum. So that means we're going to use the values on the left. So we're going to use the 1, which is a really short rectangle. We're going to use the 2. We're going to use the 3. We're going to use the 4. No 5. That's on the right-hand side. All right, so this would be 1. And then this is, and this one they did it instead of adding them up and multiplying them by the change in x, which is just 1, they have each one. You don't need to do it this way, especially because it's 1. But anyway, you would multiply the change in x times f of 1, which is 1 cubed, or 1. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So we add those all up and multiply by 1, which isn't going to change it. So the area here is 100. Right? So sigma here is 100. Instead of A, let me put sigma. Because that's a better way to think of it, is their sum. And notice that is clearly an underestimate. There's lots of parts underneath the curve that are not represented in the rectangle. And this particular graph is left and concave up. And so we'll have to make sure at the end we have summarized all the possibilities. That way you'll know if it's an underestimate or an overestimate. All right, so here we're using a right Riemann sum. So now we're not going to use the 1, but we're going to use f of 2, f of 3, f of 4, and f of 5. No 1 because the 1's on the left, and this is a right Riemann sum. So f of 2 was 8, f of 3 was 27, f of 4 is 64, and f of 5 is just 5 cubed, or 125. Add those up, and our sum is 224. Notice that that is an overestimate. You can see that the rectangles go beyond the curve, right? So this was an overestimate. How about the next one? What will happen here? This one's a midpoint Riemann sum. And then there's something important for you to write down on this one. And the important thing has the big old stars, because this is a frequent error, right? So add the two starred things to your notes. But let's first look at the Riemann sum. So I'm not going to use a change in x is still 1. I'm not going to use 1. I'm not going to use 2. I'm using the value halfway between 1 and 2. The midpoint of 1 and 2, which is 3/2. We're not using 2. We're not using 3. We're using the halfway point, which is 5/2. And then for the next rectangle, we're not using 3, we're not using 4, we're using the halfway point, which is 7/2. And then for the last rectangle, we're not using 4, we're not using 5, we're using the halfway point, which is 9/2. And then we plug that into the function, and we get our four heights, right? And when we add this one up, I won't read all those numbers. When we add this one up, we get 153. Notice it's between these two values. We have some overlap. Where the rectangle goes outside the curve, and then we have some places where we're missing part of the curve, right? And so they sort of balance each other out, not exactly, but sort of balance each other out. So the value of x used, that's our first thing I wanted to go over and have you use in your notes, is the halfway point between left-hand value of x and right-hand value of x. There it goes. And this is the part I want you to put in your notes. All right, so if the left hand is, and if you want to put the rest, you can. You definitely should have the top part. But for example, if the left hand is f of 1 and the right hand is f of 2, then the midpoint would be f of 3/2. Right? So it's the value in the middle, right, in between the two. Right? So very important, it is not the left-hand Riemann sum plus the right-hand Riemann sum divided by 2 is not the midpoint Riemann sum. Very important. The midpoint is not the average of the left and right-hand areas. It is the x value is the average of the left side of the rectangle and the right-hand side of the rectangle. But it has nothing to do with the left-hand sum or the right-hand sum, all right? So if you average those together, it's wrong, all right? Make sure you average the x values and plug that value into the function. It's not the same thing. This is where we're going to stop. This was a little longer than I planned, but you got a nice little introduction here to approximating areas of a curve. We are going to continue in the next video with finding some Riemann sums. All right? Have a great day. Bye for now.